Then we are at the point of the weak nonlinearity, and unfortunately here I discovered only later on, because you cannot really see in LT-SPICE the width and the length of the devices. You have to click on them, so there were some errors in it. So the behavior will be a little bit different than predicted, but it still will be very okay. So the design of a sufficiently low weak nonlinearity, that's what we are going to do. And this means that we are going to do something with a differential error to gain ratio. If loop gain is capable of reducing nonlinearity, then it means if we add a stage, we want this stage to add less linearity than it adds loop gain, which means that the differential error to gain ratio of a stage is a figure of merit for a stage. If it contributes nothing to the differential gain error, but a lot to the loop gain, it is capable of reducing differential gain of the loop gain without adding something to it. So that's what we mean with differential error to gain ratio. Minimizing that can be done by adding a stage, but then the stage should not add a lot of nonlinearity, because then at the end it does nothing. So we are not going to add an output stage. We're putting some stage in the middle, of course. We have already the output stage. The output stage was a nuller-like stage, which means that the stage driving it doesn't need to have a large signal, so it doesn't have a very high nonlinearity. So probably we can add gain without increasing the differential gain of the loop gain. That is important to understand. It's all, of course, it's all in the book. But I shouldn't say this anymore, FK. So the differential error to gain ratio. First, before we are going to do that, if we have biased the whole thing, then oh, no, I forgot something. Sorry, I go back. You see here the 3 blue dots. And they come, so it says that we are not completely orthogonal. And that means, well, that's clear. If we are going to add a stage, the stage needs to be biased, and we need to change the bias structure. If we are adding a stage, we are changing the pole zero pattern, and we are changing the loop gain pulse product. So, but the thing is still, if we are only to take this, going to take this action if the loop gain pulse product is already large enough. So by adding a stage, because we want to increase decrease the differential error to gain ratio, want to increase the linearity of the stage, we will probably also increase the bandwidth. And then we have to change the frequency compensation, probably. So of course, here it is, if you are an experienced designer and you can already foresee that you are in situations that weak nonlinearity will be decisive over the number of stages, then you do it, you already include such a thing in a first study of your design before you dive deep into the engineering. So that is the whole thing behind this structured design. Of course, there can be loops, there can be dependencies, but you want to foresee them, and then you are going to resolve them in a small, isolated project that is more focused on study than on product development. And if you have the result of the study, then you are going to use them for the development of your product. If you mix them too much up, you have something that is not very much plannable, and you are in fight with your project managers all the time. So the differential error to gain ratio. First, we verify everything, of course. We verify the biasing, all performance aspects, and then the nonlinearity can be reduced. So if we find too much IMD or harmonic distortion or nonlinearity, then we can reduce it by decreasing the differential error to gain ratio per stage. So in other words, making a stage more linear, without reducing its gain, its contribution to the loop gain. That's important. So that's one thing. Second, and that can be done by modifying, for example, the operating conditions or the device geometry. And of course, we can just add a stage. We can increase the number of stages, and then we should apply stages that can contribute largely to the loop gain without contributing to nonlinearity. And that means you have to insert them at places where there is not a high signal load, where there's not high voltage and current drive requirements. So for the design of the active antenna, well, you will see that verification, only by verifying the specs, we will see that we are already good enough, which means we don't need to add stages because of the nonlinearity, or change the operating point of stages or so. So let's go to that. We check the performance. Well, I think that this was already, everything was done in LT-SPICE. The results will be a little bit different if you adjust all the widths, and because there was a little bit attenuation in the current mirror because the ratios weren't correct. But okay, let's say we have no showstopper because everything works. That's also what you can say. So we have the frequency response. The antenna the noise here is like at 100 kilohertz below 10. This is the antenna referred noise, 10 nanovolt per square of hertz, and at 10 megahertz below 5 nanovolts per square of hertz, which was the requirement. Then the IMD, and I think I took the wrong one here. I should have taken a middle. This is IMD2 component, which is higher than the other one. So, but it's not 10 dB higher, and we are here on minus 67. We have a distance of minus 67, so this will probably reduce to minus 60 if I would have put the cursor on the right place. So here we have the three graphs that show us at this point that our amplifier is good enough and we can go to the next step. So the weak, there's margin. Yes, if the weak nonlinearity would be exactly on the edge, you better work with this amplifier first, maybe in optimizing the operating point or in adding stages before you go to implement the bias sources, because maybe you need another structure to bias, and then all the work is done for nothing. And that is, you know, structure design is perfect for lazy people because you never do too much. You always do what you need.